Hi everyone. Today we're going to be looking at a Math HL tutorial for your IB mathematics higher level classes. So we're going to kick it off with kind of like a little introduction to this series where specifically for these math videos, we're going to be looking at 3 of the hardest chapters in the Math HL curriculum as taught by IB. According to a student, myself, that has taken Math HL 1, and I'm currently in IB Math HL 2. And these are just like 3 topics that I've heard or that I've seen that are the 3 hardest topics that will be covered all year. So today we're going to be looking at Chapter 9 in the Haese Harris textbook, which is this one right here, by Haese Harris. This one, which is the topic of mathematical induction. So, which is Chapter 9. So mathematical induction, what is it? It's basically a method of proof. So if you have, kind of like a general rule that you want to prove possibly about mathematics, then this is the method you would use. So essentially, the way that this works is based on something called inductive reasoning, which is why it's called mathematical induction. You've probably heard about this concept in your IB theory of knowledge classes, or in your English classes, or in any other class. But IB stresses that a lot. And so basically, what inductive reasoning is where you look at a concept from a more realistic angle. Like you would look at a specific example, and then you would make a general conclusion based on the specific example to arrive at, a more broad rule that you can use and apply in multiple different contexts. So I'm going to explain now, an example problem of how you would do a proof by induction. Okay, so here we're going to start off with this right here, P of n. So P is like a proposition. This is our initial proposition for a number n, a variable n, which is an element of the integers as written here. So here's your proposition. We're going to try to prove that 4 to the power of n plus 2 is divisible by 3 for n as an element of integers. Now, how are we going to do this? Well, we're going to look at specific examples, right? So what we want to do is we want to start off with substituting substituting 1 into this expression and trying to prove that it's true. So P of 1, the proposition where you're substituting 1 as n. So let's work this out. So you have 4 to the power of 1 plus 2 equals 6, right? 4 plus 2 equals 6 equals 3 times 2. Therefore, these 3 dots means therefore, P of 1 is true, because this is divisible. 6 is divisible by 3. It's 3 times 2. Now, that's not enough. You can't just stop here and make it a general rule just because you prove that it's true for n equals 1. Now, what we're going to do is substitute k. So now we're going to do P of k, where k is a constant. We're going to want to, determine that it's true eventually. So now we say assuming, sorry. We say assuming P of k is true, because that's how this works. You have to assume that P of k is true, so that P of k plus 1 can be proved. So now you substitute k into the expression, so you get 4 to the power of k plus 2, right? So assuming P of k is true, 4 to the power of k plus 2 is divisible by 3, which means that it's equal to 3 times a number. A number, let's call it a, okay? Where a is an element of, of integers, okay? So that's what it means. We have this expression here for 4 to the power of k plus 2 equals 3a, right? Now, we want to prove this for P of k plus 1, so that we can prove that it's true for all n as an element of real integers. We need to prove that P of k plus 1 when P of k plus 1 is true when P of k is true. So here we're going to say thus 4 to the power of k plus 1. We're substituting k plus 1 into this expression, okay? 4 to the power of k plus 1 plus 2 equals, we know now we have to rearrange it. So you can write it as 2, 4 times 4 to the power of k times 4 to the power of 1 plus 2. We know that this is a property of exponents where you can divide this up into its individual powers, which equals 4 times 4 to the power of k plus 2. Now we have this expression right here. We're going to take it and we're going to, work with it. So we know 4 to the power of k plus 2 equals 3a. So that means 4 to the power of k equals 3a minus 2. We'll just rearrange that so that we can substitute this 4k into this 4 to the power of k, right? So now this expression, 4 to the k plus 1 plus 2, equals 4 times 3a minus 2 plus 2, okay? Which is equal to 12a minus 8 plus 2 equals 12a minus 6. Sorry, 12a minus 6. There you go. And since a is an element of integers, here, so 12a plus 6 is equal to, you can take 3 as a common factor, so which is equal to 3 times 4a minus 2, okay? Now, since a is an element of integers, then 4a minus 2 will also be an element of integers. Therefore, p of k plus 1 is true. Because we've seen that this expression, 4 to the power of k plus 1 plus 2, is divisible by 3, which is, it's 3 times a number. So therefore, p of k plus 1 is true. Okay, we've essentially proved it. Now we just have to write a little conclusion as to why it's true. So bear with me. And remember, on your IB exams, you're going to have to write this, your IB exams and your IB Math HL tests, you're going to have to write these this exact sentence as it is, because it's very crucial to this process of proof by induction. So what you want to say is, since p of 1 is true and p of k plus 1 is true whenever p of k is true, p of n is true for all n as an element of integers. And there you have it, proof by induction. So remember, if you ever see a problem like this, proof by induction, on math tests or on your IB exam, just remember, bring it back to basics. And remember, try to, break this expression down. Usually p of k, you put p of k plus 1, you usually want to break it down into something where you can use p of k, which you've already substituted before, right? You want to take this and you want to use this inside of it if you can. And that's always the trick for proof by induction. So remember, don't let these kinds of problems stump you in the future when you're solving a test. And from me to you, good luck on your future IB math. Thank you for watching.